over. In the past, we have talked about the types of renewable energy that are out there, and I wanted to take a bit of a different view for this day and talk about the future of energy. Talk about really in a global context what's going on and how can we get there, and what are the latest and greatest of what people are saying. How can that be kind of stitched together? So from previously, if you didn't see this, it's okay. But previously we were talking about how energy can best be understood in the context of economics. Without this frame of reference, it really doesn't make a lot of sense. You have this sort of reference list thing. And energy is used the way it is because of the way that we have our economic system. So we need this frame of reference of a system of digging up things, whether it's energy or mineral resources, production and distribution and consumption, and then disposal. So we are right now using a type of energy or types of energy that is, apologize, that is the cheapest. So we talked before about the concept of economic systems, and which, oh my gosh, I am so sorry. I thought I shut this off. Oh my gosh. So sorry. Oh my gosh, I thought I shut that off. Let me go back a little bit. Um, so we go back to this. I apologize. I thought that was off. So we are going to talk about the future of energy. We are going to frame the future of energy in the context of economics, which we've looked at slightly before, which is a system of digging up things, whether it's energy or mineral resources, and then we are distributing them or consuming them and then disposing of them. And right now we use the types of energy that are the cheapest because of our economic system. And the goods that we are looking at today are oil, gas, fossil fuels, but then also some exciting things on the horizon. The cost for energy are the same as the cost for any other type of goods. They fall into two categories: what you pay for, and then what other people pay for or that goes unpaid for. The internal costs of energy or anything are the things that you pay for. So the mining, the drilling, the distribution of this type of energy. External costs or externalities are the cost associated with the burning of fossil fuels, the mining, the drilling of fossil fuels that are not paid for by Exxon, by BP, and therefore they're not paid for by you. For example, now an externality would be climate change. It's not something that's really paid for by anyone. And so the way that we should be looking at energy so that we are able to integrate our economic system with our energy system so that we can cause renewables to cost less than fossil fuels is to take a step back from the central part here, our economic system, whether it's pure capitalism, which or largely capitalism, which occurs in the United States, or pure command, so socialism, communism, North Korea, China, etc., is to take a step back and realize that regardless of which type of economic system you adhere to, your economic system takes place in the larger framework of Earth. So Earth has air, water, soil, raw materials, etc., that are going into our economic system in this largely right now one-way throughput that ends with the depletion and degradation of our air, water, and soil and our non-renewable resources, and then pollution coming into our environment as a result of fossil fuels. If we were to do this, then we might put a price on this that is positive, put a price on this that is negative, and then our economic system will seek to minimize this stuff and maximize preserving this. And the way that you do that is to use renewables, to recycle, to reuse, and to have things that are limitless provide us with our energy. So it's that simple in terms of how we can shift to renewables, but it's that simple, really, kind of in theory right now. So what we're talking about doing is to internalize these externalities, figure out how much it costs to, say, open pit mine, to scrape off the surface of Earth, to get rid of millions of different species potentially, and replace it with a big hole and zero species. When you put a dollar value on that, when you put a dollar value on, for example, high level nuclear waste that may or may not be stored at Yucca Mountain, then you end up with putting those prices into what is right now really cheap fuel, coal, oil, natural gas, and nuclear, also sort of cheap with subsidies. And then you'll have the true cost realized, and then we can shift towards renewables. When you do this, there are environmental economists who have tried this and have looked at back calculating our economy from the mid 50s to 2000, based on looking at what we use now, gross domestic product, which you see has risen through time. And when you internalize the externalities that have gone on back through time, degradation of air, water, soil, you see that we peaked economically really in the 70s, and we've been on a downslide ever since because of unsustainable resource use, because of pollution. So if we were to abandon our current economic model, again, regardless of whether you're communist, socialist, capitalist, somewhere in between, abandon that model and use something called a genuine progress indicator, which is just a theoretical situation that some environmental economists have come up with, you end up being able to shift to renewables. Here's why we don't use renewables. It has nothing to do with technology. It has to do with the fact that the types of energy that we consider renewables cost more than coal, oil, and natural gas. Hydroelectric is cheap, but there are not a lot of sites. We don't tend to have major metropolitan populations next to raging waterfalls. So this is a bad situation that the renewables cost so much more than fossil fuels, because if we're concerned about the sustainability, the environmental friendliness of these types of energy, you see that the things that are the cheapest are the most polluting. This is greenhouse gas emissions, but I'm using it really as a proxy for all of the different types of pollution. Lignite is a type of brown, soft coal. So you see coal, oil, and natural gas have the highest amounts of pollution, and the things that we would love to use because they are more sustainable and because they are less polluting are the most expensive right now. Side note, what can we do to kind of smooth this transition as we rework our economic system, perhaps, or if we don't, at least these fossil fuels will become more and more scarce, so the price will naturally rise. We can do a lot with efficiency. This is a kind of troubling diagram that shows that this is the amount of energy that goes into our United States economy and lifestyles. You see that pretty much all of it comes from non-renewable energy. Most of it from fossil fuels, coal, oil, natural gas, smaller amount of nuclear, which is also non-renewable. It's just an alternative to fossil fuels. And we have only about 9% right now of our energy needs coming from true renewable energy. So all of this stuff goes into our economy and our lifestyles. And what you can see is that 43% is unnecessary waste, leaving lights on when no one's there, leaving the heat up when no one is there, leaving all sorts of things, cars running when we're at 7-Eleven, something like that. You see, that's almost half of the energy that we have. We could reclaim this. We could stop this unnecessary waste. Another almost half is unavoidable waste. We can't help that. So say, I don't know, a tractor trailer goes to Target and is carrying bowling balls and all sorts of other goods that are going to be sold at Target. That 18-wheeler has to go back to the factory to get more stuff. And there's nothing that Target wants to bring back to the factory. So that's an 18-wheeler that has to drive potentially a long distance empty so that we can refill it and bring it somewhere. So there's unavoidable energy. Petrochemicals, so this is some energy has to go in order to get the energy out of the system. And the useful energy that we have is only about 9%. So I don't know, you could think of this as a bad news story that we're wasting huge amounts of energy, or you can think of it as a good news story in that we can absolutely effectively address this and can also probably address some of this and smooth the transition to renewables. So this is stuff we've looked at before, but just to remind you, non-renewable energy resources are things like coal. When it's close to the surface, we mine it at the surface in open pit mines. When it's down deep, we have underground coal mine seams. And so we mine it that way and bring it up by essentially elevators. Or we do strip mining, we do mountaintop removal here. And then gas and oil on the hierarchy of things that are cleaner versus dirtier. These are much cleaner than coal. And you see, they also have a much lighter footprint on Earth to get them. It's a liquid. So it's just like a groundwater well. All we have to do is put a well in and suck this liquid up. So you can see that there's a vast reserve under here, but we're not busting up the surface and we're not drilling shafts and having to bring things to the surface. We just need some energy to pump up oil and gas, and then we can bring it by pipeline to a place where it's refined, and then we can bring it out from there. We do this on and offshore. So you see this. When you're looking at things like articles in the news or items in the news that have you freaking out about drilling in, say, the Arctic National Wildlife Refuge or drilling in different places, it's important, I think, to note that there's a pretty light environmental footprint associated with drilling for solutions and for vapors. So this is much easier on the environment than coal is, also cleaner to burn. So there's a picture just so you can see of oil and gas being mined. These are just pumps that are bringing the oil and gas up to the surface. Sorry for that. Something that's in the news that I just wanted to make mention of is that there is this concept of clean coal. And while clean coal is absolutely technologically feasible, it makes no sense to do from an energetic point of view. It's really kind of a political thing. So the way that you make clean coal is to take raw coal, very dirty, polluting thing that has a very long or hard environmental impact on Earth to mine. You pulverize it. So you've used energy to mine it. You've used energy to pulverize it into a powder. You put it into this reaction chamber with some air from the just ambient air. And then you're using a huge amount of energy to boil water to be steam. So you have steam coming in, you have oxygen coming in. You take the coal, you react it with oxygen and the water to make methane, which is natural gas. The benefit here is that you can take the leftover gases and you can remove the impurities. So you can take sulfur out, we can make matches out of sulfur. You have tar, water, things like that. You can take away, bring to a hazardous waste disposal facility. And then you have the clean methane gas leaving, that's CH4. You can put unrecycled stuff back into this reaction chamber, and then you can take the heavy stuff, chunks of rock that aren't actually coal, away. So it's easy to do this, but it uses more energy essentially than it will create out this pipe here of clean methane gas. And we have vast reserves of methane, which is just natural gas. So why would you go through all these steps to get something that we have plenty of in its natural form? I don't know. It's kind of more, again, of a political thing. So there's oil and gas. We also have vast reserves of oil and gas that are trapped in rocks. This is called oil shale or tar sand. And in this case, if we could get the oil and gas out of these rocks, our energy problems would be over. And we have for the short term, and we have vast reserves of these rocks in our country. That led in the, 50s and 60s and 70s to the looking at how can we get this out? And I'm sure you've heard the name fracking. Fracking is just a way to get the oil and gas out of rock that we wouldn't normally be able to get oil and gas out of. Certainly we couldn't just put in a pump and solution mine it. So this involves putting a vertical, then a horizontal mine shaft in. And now you inject water and you inject fracking fluids, which include prop open the pores, some sand. So you do this under high pressure. So you're cracking, hydraulically fracturing. That's what the word fracking comes from. Fracking the rocks, and the oil and gas is dissolved using these fracking fluids. Then you bring it back up to the surface, and bang, you have some oil and gas. You sometimes flare off the methane because we generate so much of it. You have holding tanks, you have the oil and gas going off to refineries, and then you have these waste storage pits where you take the water that is naturally poor quality, and then there's sand and the fracking fluids, and you allow them to settle out. The sand goes to the bottom, the water and the fracking fluids can be reclaimed and reused again. So the thing about this is that drinking water is way up here at the surface. We prefer surface water bodies or shallow groundwater aquifers that are of high quality. You hear about fracking polluting drinking water. The reservoirs where we find oil and gas are nowhere near drinking water supplies. So the problem comes when these wastewater storage pits overflow. So I'm not necessarily saying that fracking is a great thing, but I will tell you that it is something that will bring us vast amounts of fossil fuels that are domestic. And if we can get a handle on polluting groundwater, then this might be a good way to, again, smooth our transition by having a lot more domestic oil and gas. But all of these things, whether they are oil, gas, or coal, cause atmospheric pollution, and not just climate change, carbon dioxide and methane. It is also mercury, arsenic, cadmium, nickel. Radioactivity comes from these types of fossil fuels. And there is also water pollution. Crude oil, this is the map of the BP blowout in the Gulf of Mexico. Right there was where it happened. And you have this huge area where crude oil came to the surface of the ocean. It's really bad because crude oil is a complex mix of a lot of different length chain hydrocarbons. And so what that means is that some of it, like over here, is so thick and heavy that it sinks to the bottom and coats the bottom and destroys benthic shellfish, clams, oysters, that sort of thing. Some of it is in a dissolved phase, and so it can kill aquatic life that's living in the ocean. Some of it floats on the surface, so it can coat birds and anything else that has to come to the surface to get air. And then some of it actually volatilizes out into the atmosphere. So it does all sorts of things, mixes with the ocean waves. It forms this sludge that's really bad. And this isn't a talk on the Deepwater Horizon, but there was a huge blowout, massive amounts of oil spilled, people were killed. So offshore oil drilling is sometimes a fraught thing. So the point is that we have to get around using fossil fuels and as soon as possible, which is going to be guided by economics. And I won't revisit all of the things we've talked about in the past about the basics of hydroelectric, of solar. But I did want to mention that whatever it is we use for renewables for the future of energy, we have to be thinking about sustainability. Sustainability is a buzzword now, and a lot of times it is treated poorly. It is mistaken for, I don't know, huddling naked outside and not having any energy and not having any food and just living well beneath our current standard of living. I want to be very clear that that's not what sustainability is. The word sustainability refers to the persistence of a system through time. And this is our system. We are surrounded by our system. And so the goal of sustainability is to keep doing exactly what we're doing now, guilt-free, without imperiling the ability of people that come after us to do the same thing. So it requires a shift in some things that are currently unsustainable. Most importantly, environmental issues. What good is a system if you're bathed in toxins and pollutants. So we have to be a little bit better about the way that we treat our environment so that we can live in a clean environment. Health, safety, strategic concerns, regional concerns, social justice concerns. We need to be able to provide energy security in a way that is clean, that is reliable, and that is fair for all. And that's going to involve a diversity of different types of energy needs. So a couple of new types of energy that are being tested, that are some of them are around now, and you can look these up. Ocean thermal energy conversion. This works in a place where the water in the ocean gets really deep, really quickly next to a major metropolitan population. So what happens is you have working fluid, in this case, ammonia. You have ammonia in an enclosed tube, and at the surface, it's coming in contact through the tube with warm seawater at the surface of the ocean. That causes the ammonia to volatilize, to become steam. The steam is now under pressure, and you see here the steam goes through a turbine like fan blades, and that causes a rotation. When you have a rotation going on in the presence of a copper coil, you can generate a stream of electrons, which is electricity. So then you take this ammonia vapor, you bring it down to the deeper parts of the ocean where the water is cold, and you turn it back into a liquid. And then this pump brings it around again. And so you have this enclosed tube going from ammonia liquid to ammonia vapor. The vapor turns a turbine, powers a generator, and you end up with a potentially large amount of energy. This is an operational ocean thermal energy conversion plant cartoon diagram that is in Hawaii, the Makai plant, and it powers 100 megawatts, which is the equivalent of, again, as you see here, about 120,000 homes. So this is excellent. You end up having seawater powering by just the temperature differences from the warm top and the cold bottom. Using ammonia, you have it powering a lot of homes. Another thing we can do, and this is the Bay of Fundy, this is Annapolis Rail Tidal Power plant out here, put tidal power apparatus in the shallow offshore. You see that the turbines are now underwater. You have to be a little careful that boats don't crash into them, or there aren't other problems, but these things can spin when it's going to be high, when it's going to be low tide. And if you have a lot of them, they can actually prevent coastal erosion. You have these high tides, you have waves, and the drag force, these props will cause energy to be removed from the water, which will make it a more quiet water environment on this side, on the side towards the shore. So you're generating electricity, and you're also making sure that the coastline doesn't erode. Another thing that we're really doing a lot with is using biomass. So things like agricultural residue here, here's corn husks, cow excrement, any sort of organic material that we consider waste, we shouldn't be putting into any sort of hazardous waste or liquid waste or solid waste disposal facilities. What we can do is, by having some microbes be there and some water, especially in a decent temperature, you end up making methane, which is natural gas, which we can then use to create electricity. And when you are all done creating electricity, you have this slurry that can be used as a fertilizer. So we cut down on the problem of solid waste. You cut down the problem of needing fertilizers, and you cut down on the problem of needing energy. So 3 problems into 1 solution. The one thing about biomass plants when they're done on a large industrial scale is that they do have air concerns. I put this up because of the concept of carbon neutrality. So what is said about any sort of biomass energy is that it's carbon neutral. You can see here, I mean, this is probably just steam, but you can see here, there's carbon going into the atmosphere. But what is said, it's kind of like a shell game, that if you have corn husks, for example, those corn plants grew over the past several months. And so you burn the residue of them. You have taken the carbon dioxide out of the atmosphere over the past several months while the plant was photosynthesizing. Then you burn it and it goes back into the atmosphere, but it's over a very short time scale relative to digging up huge amounts of coal that was formed back in the Carboniferous period. So you can end up with so-called carbon neutrality with biomass energy in a way that you can't make that claim when you're burning coal, oil, natural gas. Sometimes, especially in industrializing countries where there's biomass energy used, you have these single species plantations that are cut down a little too aggressively, and that can end up with soil erosion. But the bottom line with regard to taking our waste, whether it is human sewage, whether it's cow sewage, whether it is agricultural residue, you reduce waste, you have carbon neutrality essentially. And if you grow different types of organisms on land and in the ocean, you can increase biodiversity. So that segues kind of to biodiesel. Biodiesel from microalgae is, and macroalgae is fabulous. Algae is my favorite form of renewable energy. I think we should be doing this everywhere. Algae has a very high oil content. Some of this algae, I think I have the next picture, Botrococcus browni, up to 70% oil. That's all essentially diesel fuel. And so you can grow this anywhere. You can grow this in sewage. You can grow it in salt water. You can grow it in any sort of wastewater. You can grow it in the wastewater of agricultural, of animal husbandry situations. It loves our waste. It loves nutrients, grows like crazy. And then we can cause it to turn into biodiesel, which is great. We can grow it in places that are naturally poor quality. It actually cleans the water as it is growing. And then what we have to do is to get the oil out. And that's the one real kind of technological problem here. Algae doesn't want to give up its oil. And so currently the best way to do it is to dry it and squeeze it, and the oil comes out. Another way is to freeze it and the cell walls crack open. You can heat it. You can use a solvent like toluene to get the oil out. So that's really the stumbling block here right now, that the algae doesn't want to give up its oil. It doesn't want its cell wall broken. But the Department of Energy did a 16-year feasibility study. And the bottom line of this study is that, yes, this is a great thing to do. It is not the case that we generate a lot of fuel by algae. And again, what we started out talking about, this is because of economics. We don't generate energy from algae because of our huge subsidies in this country that make oil, gas, and coal cheaper. We've looked at solar before, but there are some really, really neat innovations with solar. So in a conventional polycrystalline or monocrystalline solar cell, you have just a piece of glass, and one side is enriched with boron, the other side is enriched with silica, and you have the sun's rays shining onto the solar cell, and a photon will hit the junction between the boron and the phosphorus enriched side, displace an electron that's kind of seated at this junction. And you, every time a photon hits, you displace an electron. Then you have a stream of electrons. That is our electricity. This goes on at the speed of light, comes back in, more photons hit. But it's a 1-to-1 ratio, that one photon will displace one electron. And so it makes photovoltaic cells really, really inefficient. They can be down to even 17% in use. This guy, Professor Wang, he's from Georgia Tech, he found out a way to make a solar fiber optic cell that is the width of a human hair, that's hollow, and there's indium dye on the inside. And so what happens is when the sun's rays hit the hollow tube, it will bounce around. This photon will bounce around in the fiber optic cable. And every time it hits the wall of this cable, it will displace an electron. So that makes energy that is photovoltaic based or solar based much more efficient. And you can even take these, you can, the Army has bought this technology to create clothing with. and you can cause it to be um, buried, and so you have a lot more flexibility with this. So there's a picture of the solar photovoltaic. Some things that are solar based are not good ideas. I put this up because back in 2014, I was so excited about this. I was teaching about it. I was like, yay, look at this, solar roadways. And it is a giant photovoltaic cell that you lay down on the road. And this was in Denmark. And so now you have this bike path and you can generate electricity from this roadway. Since this happened, I've turned a 180 and have said, oh, this is ridiculous, because you can't put dirt or deposit anything on a solar panel and still get it to work. And you can imagine that sediment and dry deposition of atmospheric things will happen pretty quickly on this. And so the efficiency of these solar roadways went down to near zero pretty quickly. And since it's glass, they all cracked, or a lot of them cracked. So we can't do these things that don't work. It doesn't make sense. Wind turbines, we've looked at these before. These are by far the best way, aside from biomass energy, to generate renewable energy. This is a wind turbine. You got big ones, small ones, and how you configure them is based on what sort of land space you have. Wind turbines that are coincident with agricultural regions are brilliant, because you can have these wind turbines at the edges or all the way through. You can graze cattle, you can grow food. And instead of having to heat water to steam to turn a turbine to power a generator, the turbine is the turbine, the wind turbine. So these are cheap, these are easy to construct, these are applicable pretty much anywhere. They're great ways to get electricity. And so I won't go into this, but essentially you need to figure out what size of the turbine you need for your energy needs and for your geographic location. Switching to nuclear, which I'll talk about for just 1 minute. Those of us who study energy, yeah, we all kind of agree that even though we don't like it, this is the most promising energy future, using radioactive materials. I think it needs to be rebranded. I think it needs to be called something else. I don't know, neutron, or I don't know. I don't know what to say. Barium energy. Nuclear energy involves taking an atom and splitting it. Sorry for the, let's put these out. The atom being split will release energy plus a neutron, which will then go and split others. So it's this self-sustaining reaction that you then have to moderate so that it doesn't have this out of control reaction. The good thing is we have lots and lots of uranium. The mining impacts are lower than coal. We don't have carbon dioxide or other air pollution, but it's really, really expensive to do this. And this is really regulation more than the technology. There is a risk of contamination. There is a risk of water, air, soil problems associated with mining and processing. And we haven't really found, although I'll show you Yucca Mountain, a good place to figure out where to put or to reprocess radioactive waste. And then the ocean, if it's near an ocean, we can get, or a lake, we get thermal pollution. So this is what the inside of a nuclear power plant looks like, a conventional one, older one. It's pretty simple. You have this coolant in here, and the coolant comes around. It's very, very, very hot in here. And this is where the reaction is taking place. And you have these rods, these moderators that come in and slow down the radioactive reactions. So this hot coolant is in contact through this heat exchanger with a bunch of water here. It's called black water. And this steam that is generated by water being in contact with this hot coolant will turn a turbine, power a generator, and we will generate electricity. This black water needs to be cooled down. So we have a third water source. You can think of it kind of like a figure eight, but with three things. You have the coolant, you have the black water, and then you have the regular water that's coming in out of a river, lake, or ocean that cools this down. Sometimes you see this in a cooling tower. And that turns the steam back into water where it can come back around. So you just have steam being created, but using radioactive material. Nuclear power plants all over Europe, all over North America, not so much in South America or Africa. They are functioning pretty well, and they produce a lot of electricity. Maybe I'll get back to this, but we have a lot of electricity that is produced. People are scared of this. They're scared of this because of the almost accident of 3 Mile Island. They're scared of this because of the horrible accident of Chernobyl. This is a picture of Chernobyl years later. But this is a badly designed and badly run plan. If you've seen the documentaries about it, if not, encourage you to. And Fukushima in 2011 because of the Tohoku earthquake, although the International Atomic Energy Commission said that this is just operator error. Even though there was a tsunami, it still should have been the case that the operators would have known how to shut this down. So some bad situations that were operator error. We talked way back in the 90s, even this is from 2001, of where to put the waste. There's high and low level radioactive waste, and we thought that we hit upon Yucca Mountain as a great place to put this waste, long-term effective storage. And it was back, this is from, I think this is 2006, people were starting to do it. This was from 2014. We're saying yay. But now we're going to a situation where they've said no, and now it's kind of coming back. So it's just like this yo-yo back and forth about where to put this waste. Yucca Mountain remains the safest place to put it, scientists say, but it doesn't want to be, people don't want it to be stored there who live in this region. And then also there's, I think, a misperception that it's very dangerous to have nuclear waste being transported on our roadways. You think of this Homer Simpson thing where there's sloshing green radioactive material. In reality, they're just little pellets that are encased in sand, which are encased in lead drums. And if there was a tractor trailer rollover, those things would still definitely stay safe, and you can't blow them up. It's very difficult to turn them into a nuclear bomb or anything like that. So running a little bit low on time, but we are still trying to figure out how to make nuclear fusion. If we make nuclear fusion, if we take two molecules, we bring them together, we have gargantuan sums of energy that can be released in a capacity that has zero waste. So this is December 1st of this year, and we are coming closer to making nuclear fusion a reality by taking plasma and plasma of molecular hydrogen and trying to smash the two hydrogens together. This will further this diagram, which shows early from the 50s and 60s, early reactors. This is the reactors that we have around now. We have light water reactors. These generations 3 and 4 are smaller, economical, and they're not out yet. So we are not done with nuclear, but certainly we're done with it in the way that we used to do it in the 70s and 80s because of the problems associated with it. Which brings us to the kind of last thought of hydrogen. Is hydrogen going to play a role in our future of energy? Some say yes, some say no. This is a great idea. Look at what's going on here. You have hydrogen going in, and the hydrogen goes in, and hydrogen is atomic number of 1. So it gets split into protons and electrons. The electrons get harvested. There you have electricity. The protons go through a membrane, and then these things get recombined, and you have when air comes in, you have just water vapor leaving. So this is a brilliant thing in theory. The stumbling block here is that there exist no vast reserves of hydrogen in this form, H2. There is hydrogen, but it's locked up in other molecules on Earth. And so what we've historically been doing is taking methane, which is natural gas, that's a fossil fuel. We use a fossil fuel to pluck out the carbon, and now you have hydrogen. So you're essentially using a fossil fuel to modify a fossil fuel to pretend you have a renewable energy form, when really this is nothing more than a form of energy storage. However, there's been some interesting innovations. This gentleman, Daniel Nocera, he has a joint appointment at Harvard and MIT, and he's developed something called the artificial leaf. Using the same equation that governs photosynthesis, he is finding, he has taken water molecules, plucked the oxygen off the hydrogen using solar energy, low temperature, geochemically stable materials. Now you have hydrogen that you can use for hydrogen fuel cells. I'll show you a couple of applications. Or you can take the hydrogen and the oxygen at night, recombine them, and that also generates energy. So Dr. Nocera has taken what was once a boutique form of energy, photovoltaic, solar, and turned it into something that is a true contender. And we can use these in cars, we can use them in buses, we can use them in mopeds. And this just came out this year too, microbes are being genetically modified to produce hydrogen instead of oxygen when they're exposed to air. That would be another really, really exciting way to get hydrogen. If we can get hydrogen from water or from little microbes, then we are good. Right now, a lot of people, Volkswagen here, and one of the people, this is Martin Winterlaken who's the CEO of Volkswagen, said, we're never going to have hydrogen fuel cell cars. So I don't know. We can have stationary fuel cells that are hydrogen based. We can use fuel cells in telecommunication, again, stationary. We can use them in micropower. If you have a laptop that has a hydrogen fuel cell, it will not need to be charged all week. So fuel cell technology is being used a lot in the military for its reliability. It's not something that generates heat. It's efficient and it is secure. But they're heavy, they're cumbersome, and they are not really durable in terms of the long term of recharging them. And mostly, back to the first slide, they're super expensive. So batteries are where it is at, and we are coming up with a number of high density metallic materials that are highly porous, that are able to store larger amounts of energy. But this is a tough thing. Everybody has a different idea of what the battery should be. And there are all these metals that are being used, and they have all these different structures. So how do you standardize this? We need to be standardized. My bet, if I were a betting person, and this is where I put extra money when I want to play the stock market, is on the material graphene. Graphene was developed by these two engineers, physicists, sorry. It's really cool. They would sit around, and they were from the University of Manchester, They'd sit around on Fridays and have a beer and try to solve the world problems. They decided, oh, we need to have a method of energy storage. So they were thinking about it, and they decided that if you had a two-dimensional molecule that was carbon-based, you would be able to store a huge amount of energy in it. So they took just regular graphite, your pencil lead, and they took Scotch tape, and they stuck Scotch tape onto graphite, and they peeled away what was indeed a two-dimensional molecule. And this is unbelievable. I could go on about this all day, but graphene is it's super lightweight, flexible. It's 200 times more bulletproof than Kevlar. So it's being used in the military. They're looking at it. It's expensive. Again, the only thing, charges really fast, has a huge amount of energy, and it's supposed to be on the market next year. This is a picture of the molecules. And this is a little video, 7-minute video we won't watch now, but you're welcome to later, that shows the applications of graphene. So this is really exciting to me, that a new battery that is made of carbon, which is a plentiful molecule, or atom rather, on the surface of Earth, would absolutely revolutionize the future of energy. So to me, the future of energy doesn't involve new technologies of solar versus wind versus hydropower. It involves a great, great way of storing energy. And so, yeah, look for graphene in the future because they were invented 2004, but it takes a while to get things out and they're expensive, but they're going to be here. One last note before we end is that oftentimes you see places like Denmark or Finland or Norway talking about their fabulous, carbon neutrality and how they don't use any fossil fuels. I am so unimpressed with this, and that is not at all to be against these countries, except to say that these three countries, each individually, represent 0.07% of the global population. Iceland talks about how it is virtually all renewable energy. It is less than 1/100 of the global population. So to me, that is not impressive just by virtue of the numbers. We have a lot of people on Earth, and these are from 2019, the prospects of what the maximum capacity estimates are for people. But right now we're in a situation where China has 1.45 billion people, 19% of the global population. India is 1.4 billion people, 18% of the global population. We are third in the United States with only 300 million people, which is about 4% of the global population. In order to fix energy, we need to fix these two countries. And these are some numbers from the China National Petroleum Commission, looking at forecasts. I won't go into these. And two is BP, our company, BP, US company, looking at the future energy forecast in China. And there's going to be more renewables, it seems, in China by 2040, but it's not at all going to take the place of coal, which is staggering amounts of coal. And this is, again, the demand for power in China under a number of different scenarios. You see it's a lot of coal and nuclear. So the bottom line here, and then we can move on, is to talk about the summary that we need to shift to renewables. But the way that we're going to shift to renewables is not by developing more technologies in renewables. It's to develop batteries. And there's not going to be a silver bullet. We're going to have a mix of renewables based on what's going on in each different country. And we have to get to a situation where the subsidies are withdrawn from the oil and gas industry and shifted towards making these other forms of energy competitive economically, and then making these batteries competitive so that we don't have a situation where we are in a mess environmentally. So I will